There's a lot of amazing and fantastic things occurring every day, everywhere, just yearning to be explored. It can seem in today's times it's harder and harder to find such beauty in the world, but that doesn't change the fact that it's there. The mundane yet fascinating functions of the everyday life are often overlooked, continuously plugging away in the background as everything moves about around them. For this reason, it seems appropriate that the first step on our journey of discovery is about the very thing that lets us observe such intricacies in the first place. I'm of course talking about light and why it's so interesting. You probably don't think about why you can see things too often, or even why light exists, but it plays an integral role in just about everyone's life. It's how we observe our surrounding world and absorb most of our information, and it plays an essential role in our society. But if someone asked you what light was, where would you begin? To a scientist, the term light usually has a broader meaning than just a thing that facilitates our ability to see. Light is almost always synonymous with the entire spectrum of electromagnetic radiation, spanning from radio waves all the way to the sinister gamma rays. Despite their differences in behavior, the different forms of electromagnetic radiation are all of the same energy or the same thing. Microwaves, radio waves, X-rays, and ultraviolet are all sides of the same energetic die, with one of those sides being the visible light that's letting you view this video right now. But still, what exactly is it? At some point in your life, you've heard the term light waves or waves of light, and light is presented as such, a wave. But in reality, electromagnetic radiation is a quantum object and behaves as both a wave and a particle, but it is also neither. Light waves don't behave like the waves we are used to. Unlike waves found in our world, light doesn't have length. Light is actually a singular oscillation of both magnetic and electrical fields traveling through space. Now, if we were to plot this movement, we would very clearly see a wave function and shape, therefore it's understandable to visualize and classify light by the length of their wave period, or how far this point travels through space after completing one full oscillation. But this fails to explain the interaction of light with matter. Normal waves apply their energy with time, continually increasing the amount supplied. Light, however, despite behaving like a wave, doesn't do this. All of the energy within light is passed off seemingly instantaneously in known and distinct amounts. These units, or quanta of light energy, are called photons and represent the particle nature of the way light behaves. All light, all electromagnetic radiation travels in the form of photons, these singular packets of energy. So unlike normal waves where an impulse or the force applied by the wave is continuous for the entire length of the wave, our perception of a steady light source is just a constant stream of photons with the same rate of oscillation, one after another and another and another. So light, or photons, exist as an oscillation in space that we can describe as a wave but behaves as a particle. But why does it exist? Where does it come from? Energy is the lifeblood of the universe and is constantly being exchanged and moved around. You may already know many different ways we can transfer one energy type into another. Matter is itself pure energy in a highly condensed form, and since matter is energy, it too needs a way to transfer itself. So anytime an atom, molecule, or a bit of matter needs to release some kind of excess energy, it can either transfer it thermally to a neighbor atom or molecule, or, more relevantly, it can release it in the form of light or a photon. In order to fully understand this, we're going to have to crack open an atom and see what makes it tick, how it behaves. So let's start here. A simple Bohr model of hydrogen with a single electron orbiting the proton in the nucleus. These are the fundamental building blocks of the universe, and if we understand what happens here, we can understand what happens everywhere. Now, normally an atom exists in its ground state, right here with the electron at this defined distance from the proton. If nothing interacts with this atom, it will exist like this, possibly until the end of the universe. Now, as one might imagine, if hydrogen can exist in a ground state, it can probably exist in another state. And sure enough, an atom can become excited if it receives the correct amount of energy needed to excite the electron into a further orbital or distance from the proton in the nucleus. When an atom is no longer in its ground state, it is in what is known as an excited state, and a principle of the universe dictates that excited states, or a system with more energy, is never as stable as the ground state. So, to return to stability, the excited electron can either react with another atom, or it can simply return to the ground state and release the excess energy received. And this, my children, this process of an atom returning to its ground state, is where essentially all light comes from. So light comes from the excited or energetic atoms and material returning back to their ground states. But why does this process produce a photon? How do we go from an electron to light? It doesn't really make sense if you think about it. And that's because we are thinking about particles when we should be thinking about waves. As I mentioned previously, light, like all quantum objects, behave as both particles and waves. Even here, both the electron and the proton are behaving as both particles and waves. Now, due to the proton's large mass, it doesn't behave too much like a wave, so we can continue to think about it as a particle. The electron, however, has 1/1837th the mass of a proton, and so behaves very much like a wave. So what we imagine as a particle orbiting in a nucleus actually looks more like this, a wave function of the electron possibly existing in all possible points within a contained volume. Despite its strange appearance, this can actually be represented mathematically as a proper function. Now I won't overwhelm you with the mathematics of it all, but this means that we can think about electrons as a simple sine wave to help our visualization. When talking about waves, there's a concept called overtones that needs to be understood. The rate at which a wave oscillates every second is called its frequency. If you take that frequency and you multiply it by an integer, so 1, 2, 3, and so on, the new resulting frequency is what we call an overtone. You can think of this as the different octaves to the same note played on a piano. Because overtones are oscillating faster than the fundamental frequency, they are more energetic, or they can deliver more energy. Now, when we think of electrons as wave functions, the ground state is their fundamental frequency, and their oscillations reflect that. When they receive excess energy, then they transition into an overtone, or an excited state, with a new wave function that possesses more energy. Eventually, the electron will return to its ground state, and as it does this, its wave function will wrap down to its fundamental frequency and emit that extra wave energy in the form of, well, a wave of light. And finally, we understand the birth of photons. Every time an electron's wave function collapses back to its ground or lower energy state, it produces another wave, or light, to compensate for this loss of energy. And with this knowledge, we can finally look at the different mechanisms that produce the different types of light. After all, light is a spectrum with theoretically infinite possible wavelengths. So how do we produce one or the other? What distinguishes one type of light from the other is how much energy the respective photon is carrying. The energy of a photon is dictated by the rate or frequency of its oscillations, with faster oscillations providing more energy. When we visualize light as a wave, this can be represented by its wavelength. Therefore, light with shorter wavelengths contain more energy. So, in order to produce a photon with higher energy, the electron itself that produces it needs to contain more energy. And it does this by being excited into even higher overtones or even further orbitals. That way, when the electron returns to its ground or lower energy state, it must emit even more energy in the form of light. The different ways atoms become excited are generally the criteria we use when we describe light sources and where light comes from. There are two principal sources of light: incandescence and luminescence. Despite each using different mechanisms, at the end of the day, they both mean the same thing. An electron gets excited and then returns to its ground or lower energy state. Incandescent light is the most common light in the universe, and its biggest player is black body radiation. Now, black body radiation is another very interesting concept on its own and possibly deserves a complete separate video. But to be brief, electron excitation for black body radiation comes from the temperature of matter itself. All molecules and atoms are vibrating, moving, and spinning about in all matter. As they bump into each other, they can transfer some of their internal energy to one another. This new excess energy can then be used to excite an electron into an excited state. And as we learned, when the electron returns to its ground or lower energy state, it produces light. Therefore, hotter and hotter temperatures means more and more energy can be transferred amongst the molecules. This creates greater electron excitation, which produces not only higher intensity light, but also brighter light, since more energy in an object also means more molecules and atoms can become excited. This is actually the principle we used for our older light bulbs to work by superheating a small wire filament until it was hot enough to glow. Luminescent light is the second light source and is comprised of light not produced by heat. There are three main subcategories, and again, I remind you, at the end of the day, they all simply describe excited electrons moving to a ground or lower energy state. Now, the first subcategory comprises changes to chemical bonds in chemistry. We can see this happen in triboluminescence and chemiluminescence, where an alteration in the chemical makeup of matter changes or lowers its internal energy, thus emitting the excess energy in the form of light. The second is electroluminescence, and this is what we use for most of our lights now. This effect occurs by passing other electrons or a current through a material. Now, depending on the mechanism used in the light bulb, this current will excite electrons who then subsequently fall back to a ground state. Light bulbs like LEDs that use this method are far more efficient than incandescent bulbs, as very little of the energy supplied to it is lost to the generation of heat. The third luminescent light source is the reemittance of light, and this is composed of two more subcategories: fluorescence and phosphorescence. Both of these principles involve matter absorbing light or a photon themselves and then emitting it away. Fluorescence is interesting because most of the time the light it reemits is a lower energy than the light it absorbed. This makes certain minerals glow under UV light, and this is what was happening at your local roller rink or bowling alley back in the 90s. It's also what's still happening in fluorescent lights today. Electrons shoot through ionized air with mercury atoms, which are excited by electroluminescence to produce UV light. This UV light is then absorbed by a phosphor powder, not to be confused with phosphorus, on the inside of the bulb, and then re-emitted as visible light. Phosphorescence is the final light type to discuss, and it's the same principle as fluorescence, but these atoms for some reason are able to take their sweet time when transitioning back to their ground state. As a result, a phosphorescent object appears to glow as every single atom within it decides to return to its ground state at its own pace. These different light sources account for essentially all the light in our universe, and certainly in our society. The remaining energetic light types, like X-rays and gamma rays, are generally formed by different processes, and I could probably spend another 15 minutes talking about them, but the overarching theme to both these processes, and the ones mentioned previously, is that when matter receives or is in possession of too much energy, it will eventually release it in the form of light. To cap things off, so now you may be wondering, if light comes in a spectra of different energy levels, why do we see the light that we see? You've probably heard of the mythical mantis shrimp with its 12 color receptors for all the fantastical colors it could possibly see, or that birds and bees can see UV light and maybe you felt a little left out. After all, why do we just see the simple visible light spectrum and not some other kind of light? Well, the easy answer is that we simply evolved to see that part of the spectrum, and nature decided there's no evolutionary benefit to being able to see other light waves. But the truth is there is no law dictating which part of the spectrum an organism can see. It's all circumstantial. The circumstances or reason that we see what we consider the visible spectrum is because of our own atmosphere. Matter absorbs light. That means the matter in our atmosphere, as non-dense as it is, absorbs some light as well. And it's better at absorbing some wavelengths than others. If we plot out all the different wavelengths of light coming from the sun and their absorption by the atmosphere, we'd find a large dip of absorption in the visible range. Since this is the most abundant light with the highest energy or smallest wavelength, organisms on this planet have evolved to be sensitive to it. This generates interesting thought experiments, for if we did ever meet an intelligent life, their view of the universe would be heavily dictated by the composition of their atmosphere, and who knows how that could change someone's perception and attitude towards the universe. And that's just one of the many different ways you, me, and life on Earth is unique.